Good evening. Today we'll discuss divergence and curl in greater detail. To look at that, let's start with fluid flow. So, for example, if you consider water flowing from a faucet, um, let's ignore gravity for the moment and assume assume that this is flowing with constant velocity. We can describe this in terms of its current density. And by current density, we denote it with J, a vector. It is a measure of the rate of flow of water per across a surface per unit area per unit time. So it's a measure. This current density is a measure for the rate of flow. Now, if you want to describe the flux, think about having a screen or a surface that is at an angle theta, right, as the water is flowing down with its current density. Then when there is a screen like this and water is going through that, there is a component of this current density that's or the velocity of water that is flowing across the screen here. This component is not useful in increasing or in contributing towards the rate of flow across the surface. So there is a component of current density that makes water flow along the screen. And whatever is this component is not contributing to flow across the screen. So there is only a certain component, and that would come out to be j cosine theta. So if we want to define flux in general, we can define flux as, for example, whatever is the current density, J. This is related to the velocity of the fluid, which is given by V. So J is equal to rho V because it is measuring the rate of flow of water across across the surface per unit time per unit area. So that's how we are getting J is equal to rho V in case of water, for example. And if I have a screen, only a part of this velocity is contributing for flow across, because some part is contributing to flow across the screen, right? So then I can define an area vector for a surface like how we had defined in our last lecture with respect to surface integrals. I can define an area vector, right? That would be following, if I go around the loop in a right-hand fashion. For example, here, if I go around the loop this way, the area vector would be pointing perpendicular to this, right? So then I can define the flux as J dot this area of the screen. So that is nothing but magnitude of J, magnitude of A, cosine theta. So that's what I meant by only a part, a component of the current density is contributing to the flow across the screen here, right? But we want to describe this flux, but we don't want to explicitly introduce surfaces like this. We don't want to deal with this aerial term. We want to describe this flux so as to put it at every point, rather than explicitly introducing a surface like this. Here I introduced a surface explicitly that is at an angle theta, and then I'm talking about flux. So I have this area here, right? So we are basically looking for a way to express the essential quantitative facts about flux in the limit of arbitrarily small size. So I want to go down to a smaller area element, dA, and then I want to have a purely mental construct. Through a purely mental construct, I would like to encapsulate whatever this flux is telling me without explicitly having to introduce a surface like this, right? So if I have a surface, I can break it up into smaller parts to know the flux through. I can break this surface up into smaller parts, and I can call each of these as dA, right? And I can go around the surface, integrate each of these elements, j dot da's, the tiny elements from each surface element, right? I can take the flux and essentially add them up by integration. That's what we're doing. Through integration, what we're doing is we're taking flux through each element and adding them up. And that's how we get this surface integral, where we're adding up flux from each and every tiny areal element. So now imagine that, for example, you have, imagine a sphere, right? Now, if there is some flow into it or out of it, right, we would like to describe that flux, that is the flow into the sphere or outside the sphere. So there could be flow into it or flow out of it, right? So we want to encapsulate this idea of flux for an arbitrarily small point without introducing any surface. So to do that, notice that I can simply write that this j dot dA, if I take the flux over the surface of the sphere, maybe, right, then that equals volume by dt. That is because if there is a flux into it, then let's say this is a fluid flowing, let's consider a fluid flowing. So if there is flux into this, then water is going in, right? Water is going in. If there is a flux out, water is flowing out. So if I can know the net flux, then I can know how the volume of water inside the sphere is changing, right? For example, an easier way to think about it in an analogy is that, for example, if you have a classroom, right? If you have a classroom or a building with so many doors, there is a door here, there's a door there, there's a door at the back, right? With so many doors, then we can keep a count of number of people entering and exiting the building. So for example, if you enter the building, I keep a counter of +1, right, for in, and -1 for out at each door. And then by keeping a track of this flux, I can see how the number of people inside, how they're changing. In a similar way, here by keeping track of flux into it and flux out of it, the net flux, by keeping track of net flux, we can see how the volume of water within this sphere is changing. So notice that I have here a surface integral. That means we are integrating over the surface of the sphere. That means if I take a point here, right, because this is a closed surface, remember our convention, if it is a closed surface, then the areal element is pointing normal to that surface. If it's an open surface, you can define it by going around the perimeter, like how we have seen in the last lecture. I'm not going to repeat that here, but we are essentially integrating over the surface that is enclosing the sphere, and that's what gives us this net flux. So if I want to know this net flux from this surface, then let's say not necessarily a sphere. You can take any surface. For example, let's take a potato, right? So let's say something like that, right? So imagine this to be a three-dimensional potato. So if I want to know the flux, I would like to find out the surface integral of j dot dA. That's what is going to give me, it's like the counter we keep at each door. It gives me how much water is going in, how much water is coming out, the net flow in and net flow out. We're keeping a track of that. So to do this, what I can do is I can divide this surface, right, into smaller surfaces. So I can say divide the surface into a smaller surface. Let's call this, S1. maybe, right? I divided this into smaller surfaces, so I can do, for example, I can show you another smaller surface, right, with infinitesimal volume S2. So I can divide that into so many of those slices. So essentially, think about cutting this potato into small chips, right? Um, so, and then I can calculate the flux through this surface, for example, surface S1. So I can calculate the flux through surface S1, J dot dA, right? Similarly, I can calculate the flux for the next one for surface 2, right? I can calculate the flux for this. So this is J dot dA S1. This would be integral S2 J dot dA. But notice that, like how we talked about people going in and coming out, look at S1. So this is going in, right? This is coming out. So whatever is coming out for S1, right? Out for S1 is in for S2, right? So for that, for S2, this is in. This is in for S2, and this is out for S2. Similarly, if I call this S3, right, whatever is out for S2 would be in for S3, right? So essentially, if I add up all these integrals over each surface, S1, S2, S3, if I do the J dot dA, the flux, all these intermediate terms, whatever is out for S1 is in for S2, so they cancel out, right? So they keep canceling out, and what I get is essentially what is entering at the top and what is exiting at the bottom. Whatever is in the middle, just like how these two components get canceled out, they get canceled out. So I can write over the entire surface S, that is this red line here. So I can write this red line here of the potato, the overall surface of the potato here. I can write that flux J dot dA over the potato surface as a summation over I of I going from 1 to n and Si J dot dA. So I'm cutting this potato into tiny chips, right? There is these chips, and I'm labeling them as I is equal to 1 to n. And so if I add up the flux through each of this, I'm going to get the flux overall through the surface, because all these intermediate terms, in between terms, they cancel out, because what is out for S1 is in for S2. So then I can write J dot dA over the entire surface as a summation of I is equal to 1 to n smaller surfaces J dot dA. If you want a better three-dimensional picture, for example, let's say I have some potato here. To see a better three-dimensional picture, maybe you can look at a small cube, right? And I can divide this into small cubes. I can divide this surface into small cubes, and I can draw another cube here, right? I can chop this up into small cubes like this, right? So if I look at just these two cubes, let's call them A and B, right? So for example, if there is flow coming in this way, right, that's in for A, for this face of A, and then there is a component that goes outside A. If I calculate just the flux over the surface of cube A, and whatever is going out, so these two cubes are adjacent to each other, right? So these two cubes are adjacent to each other, A and B. I'm just drawing them apart to show you how these different flux elements cancel out. So whatever is coming in is out for B, for A, and this component is what is in, right? So if in is positive and out is negative, or the other way around, whichever convention you use, these two sides, because they are attached, right, they get cancelled out. Similarly, if I have a cube next to B, right, and call it C, these two cancel out. right? So overall, if you divide this potato into small cubes and do the flux over each cube and add all those cubes up, you essentially get the flux over the surface enclosing that potato, and that's what this is telling us, right? So if we want to divide this into small volumes, tiny and tiny volumes, we want to say if the total volume of this potato is V, I want to divide it into small portions, delta V, into n cubes, right? I want to divide this huge potato into tiny cubes, so I divide that into n cubes. So the volume of each cube would be V over n. But if we just do this, there is a problem, because if I keep increasing n, this volume becomes so small that the flux of each single cube becomes so tiny that all of them almost go to zero, right? So hence avoid going to zero, right, and to also include this effect of the proportion that there is to volume, what we can do is, instead of just looking at J dot dA, we can instead look at um, over SI J dot dA divided by delta V. Instead of just looking at this element, I'm going to divide it by delta V, because if I divide it too small, if I let delta V go to zero, right? If I let delta V go to zero, then I run the risk of this J dot dA. Each of those elements, they're too small, so each of them goes to zero, and what I'm doing here is simply a sum of zeros. So instead of doing that, to include the proportionality to element, we are dividing, we are getting per unit volume sort of a thing. So we are dividing each flux term here, we are dividing it by our delta V, right? And the limit in which this delta V goes to zero, the limit in which this delta V goes to zero, we are not actually making it zero. We are doing a mental construct here. That is, we are assuming that we are able to divide this into infinitely small elements. It's potentially divisible. It's a mental construct. It's a potentially divisible into infinitesimal volumes, but we are not actually doing it. That's what this tends to zero means, right? And and then if I take this, I get basically divergence of J. So essentially, what we're doing is we're taking a volume and we're shrink wrapping it to a small tiny point, and asking how the flux is from the tiny point, right? And we're defining this J dot A by delta V to describe the flux, right? Because if I add up all these J dot DAs, I get the overall flux going through the surface of the potato. So I'm defining divergence this way. So this is the fundamental definition of divergence. The fundamental definition of divergence is, in the limit the small volume element goes to zero, what is the flux per unit volume, right? So if I take a volume with delta V, J dot dA divided by delta V, right? So this is how we are defining um, this divergence. So this is for a single element. So we looked at the potato, right? We are looking at these small tiny cubes in the potato. So when I say S delta V, right, that is for one single cube within this potato. So if I want the overall flux that is going through the surface of the potato here, like we have seen on the last slide, I have to use this. So if I want the total S of J dot dA, right? So that is simply equal to uh, a sum of all these tiny cubes, right? A sum of over each surface Si, right? So if this is the ith volume element over the surface, I have J dot dA, right? And now if I um, change this into same summation I is equal to 1 to n, instead of just simply writing j dot dA for one surface, I'm going to divide it with delta V and multiply it with delta V, and set a limit that delta V goes to 0, right? So these two things are the same. Essentially, what I'm trying to do is I am trying to describe the entire flux going through the surface that is enclosing the potato by dividing it into smaller and smaller cubes. So if I divide it into small cubes, I can calculate the flux for each small cube, add all these tiny fluxes up, then I can get the divergence this way, right? And and I'm trying to relate the divergence to the total flux out of the potato surface area. This is the surface of one tiny cube that we are dividing the potato into, right? So now by doing limit of delta V is equal to tends to 0, this is essentially, if I move this limit delta V there instead, and I write it as, sigma I is equal to 1 to n, right? Limit delta V tends to 0, j dot dA by delta V. This is a divergence of J. This is how we define, this is how we fundamentally defining divergence. So this is the fundamental definition of divergence. In the previous lecture, what we looked at when we meant divergence was we were introducing it. So we looked at in Cartesian coordinates, but fundamentally, this is the definition of divergence. And from this definition of divergence, then I can write this as del dot J. But my limit delta V is going to 0, and I'm summing over as limit delta V is going to 0. So I'm using this mental construct to convert this summation into an integral and write this as divergence of J dV, right? And this is over the entire volume of the potato. So then I can write over the entire surface J dot dA is equal to the volume integral of divergence of J dV. And this is nothing but Gauss's theorem. So Gauss's theorem follows from the fundamental definition of divergence, right? Just to recap what we have just done, let's do this again so that you understand it better, what divergence is, because it's very important to understand divergence for this course. Our goal is to describe the flux of a flow, of a fluid flow, for example, but without explicitly introducing a surface, like how we introduced a surface at an angle theta while trying to look at the flux of water flow. We want to describe this field at each point, this flux at each point in the limit of arbitrarily small size, right? So we want to encapsulate all the essential aspects of flux without explicitly introducing a surface. To this end, we first noted that if I have a surface, if I have a volume rather, sorry, if I have a volume like a sphere, then I can count what is coming in and what is going out. So I can keep a track of flux, and this flux tells me the amount of the rate of change of volume within this sphere. And from there, what we said was this flux is nothing but integral of J dot dA over the surface. But to compute this overall flux for any given surface, we can divide that volume into tiny volumes. So here we have a volume, right? That is, I have a sphere, that is the volume. And I want to calculate the flux, I have to integrate around the surface that is enclosing this volume. And that's what we mean by this surface integral here. right? We are integrating over the surface and closing the sphere. To do so, what we can do, not just for a sphere, but for any shape, for example, this shape, potato, I can divide this into tiny volumes, right? I can divide this into tiny cubes. And, so I'm dividing this volume, this entire volume, into tiny cubes. And I'm taking one cube, for example, I'm taking one cube, right? And I'm calling the surface integral over this tiny cube, which has a volume of delta V, which is the total volume by the number of elements you have. So I'm taking this tiny volume and I'm calling the flux for that tiny volume as SI J dot dA. So I am integrating only for this tiny volume element and calling it J dot dA, right? So if I make this volume delta V go to 0, then what happens is that in that limit, this each of the elements may give rise to zero flux. So to avoid that, we are scaling this by dividing it with delta V. Now the net flux through the entire surface of this potato, right, is equal to summation of I is equal to 1 to n, the net flux over each tiny cube. We're adding them up. And to describe this, each single element divided by delta V, we're defining in the limit delta V goes to 0, we're defining this as the divergence of J. So we are reducing the volume to a small and small size. Ideally, we would like to go to a single point, right? But it's only a mental construct. We're completing that only mentally, not actually. So this is the fundamental definition of divergence. Given this fundamental definition, we can divide this with delta V, right? And in the limit delta V goes to 0, right? This part is the divergence, right? Del dot V. And then I have another delta V, and in the limit delta V goes to 0, the summation over this is simply an integral, but this is a volume integral because it's over delta V, so you have del dot J dV. So you are relating the surface integral, the net flux, to the divergence, right? Or as it is in the textbook, right? You can sort of think about as the if I integrate over, this part is telling me integration over faucets within the volume, right? So if there are more faucets, there is net flow outside. So you're looking at the faucets within the volume or drains within the volume, sinks within the volume, and then you're looking at how many people are entering, how many people are going out, similar to that, to get what is the net flow through the surface. That's how. That's why we say divergence is describing the net flow. So that's the fundamental theorem of divergence, or Gauss's theorem, right? So now we can look at the Cartesian coordinate system and see how to derive divergence in such a Cartesian coordinate system. So I refer to these small tiny cubes within the potato. So let's look at one such tiny cube within a volume, within a potato, and see what would be the net flow through that, right? So let's draw a tiny volume here. So I'm just going to draw one tiny volume. So this one tiny volume within the potato, right? If I divide that into tiny cubes, I'm looking at one such cube. I'm zooming into it. So let's say it looks something like this, right? So let's call this A, B, C, D, the face ABCD, and at the back, let's call it EFGH, right? So if I just look at the flow, so through say face EFGH. So if I look at the face EFGH, that is this one. If I look through this, right, this is situated at the origin, this face, for x is equal to 0. And we have done the surface integrals earlier in the last lecture. So you know that here the area element is pointing this way, right? But if we look at the net current density, net flow going through this, right, that would simply be if I have rho v Vx at x is equal to 0 dy dz, right? We get only the x component because the area element for this face is pointing along x, correct? And similarly, if I take this one, the face ABCD, this face ABCD, for ABCD, now I still have the same thing, but except my flow is rho Vx at x is equal to dx, because this is a tiny volume. Remember that this is a tiny volume within the potato, so the side of this cube is delta x, and the volume of this tiny cube is delta v. So it is x is equal to dx dy dz. So I can expand this further as rho Vx at x is equal to 0, right, plus dou by dou x of rho Vx dx dy dz. I'm just using Taylor expansion, right? So if I want the net flow through this x-axis in this direction, right? If the flow is coming in here, it's going out here, right? What is coming in for EFGH is going out for ABCD. If you consider it the other way, if it is flowing this way, what is coming in for ABCD is what is going out for EFGH. So I'll have to subtract. So if I do such a subtraction, I can see that the net flow out through the front and back faces, through front and back, would be essentially this term would cancel out, and net flow would be given by dou x rho Vx dy dz, dx dy dz, sorry. So this dx comes from the Taylor expansion here. So we have dx dy dz. So the same thing would happen for the side faces, right, and the top and bottom faces. So we can, by the same analogy, we can write for the side faces, right? For the side faces, the thing that is changing is y. So I would have dou by dou y, rho Vy, again dx dy dz, and for top and bottom, I would have similarly dou by dou z, rho Vz, rho Vz dx dy dz. So if I want the overall net flow, basically I add these up. So then I would have, let me clear the slide here. Then I would have essentially dou by dou x, rho Vx, plus dou by dou y, rho Vy, plus dou by dou z, rho Vz, right? Dx dy dz, right? So if you look at this part, right, rho is the density, it is a scalar function, right? It need not be a number, it could be a scalar function, especially if it's a compressible fluid. Then I can write this rho v vector as rho times rho of xyz in general, vxi plus vyj plus vzk, where velocity is the vector there, right? So then I can write this rho vx as dou by dou x. The ith component is rho vx, y component is rho vy, z component is rho vz. So you can see that this is nothing but dou by dou x along I plus dou by dou y along j plus dou by dou z along k, this operator with rho and v. Right, I can write this as rho and v, and we know that this is the del, and so this is the divergence of rho v. So the net flow out, without using the definition of the gradient, we have shown that the net flow looks like this, just by considering Taylor expansion, and from there we were able to see what divergence is. So as we will see later, in case of other coordinate systems, be it spherical polar or other coordinates, the gradient does not need to look like this. In fact, it will look very different in different coordinate systems, right? So that tells us about divergence. And once again, to repeat, the fundamental definition of divergence then is that I am integrating over the surface that is enclosing the potato volume. J dot dA is equal to the volume integral of gradient of J, the net flow, times dV. So that is Gauss's theorem, or the fundamental theorem of divergence that follows from the fundamental definition of divergence. Now let's switch gears and look at what is curl to understand fundamentally what curl means. To do this, let's take a step back and look at a very simple thing, that if I have a function f of x, right, over an interval a b, right, then I can write the average of this function as 1 over b minus a integral a to b f of x dx. And this is very easy to prove. For example, if I have, let's say this is f of x and this is x, right? So let's say the function is somewhere like that. So when we say when we say integrate, we are basically dividing this into tiny fragments, this curve, right? And each of these fragments, excuse me, and each of these fragments are delta x, right? And we're looking at the function between 2 points a and b, right? So this, if I divided this into n tiny segments, then delta x is essentially b minus a by n, right? So then if I want to know the value of function for each of these grids, right? Let's call this x1, let's call this x2, so on and so forth, right? So if I want to know the average, then I can just simply write it as f of x1 plus f of x2, right, up till f of xn divided by n, right? But from here, I can see that n is nothing but b minus a over delta x. That's how many segments we have divided it into. So then I can, instead of this n, I can write it as b minus a divided by delta x, which gives me this function at x1, at x2, so on and so forth, at xn, the value of function in each of these segments, right? And because these segments are very tiny, in each of these segments, it's a flat line. We're approximating the function to have the same value, right, while integrating. So this is multiplied by delta x b minus a. So in the ideal limit for integration, what we want to do is we want to integrate till delta x goes to 0. The line, the curve is this curve of f of x is potentially divisible into infinite points, but we're not really dividing it in actuality. We're just using it as a mental construct. So if I do this in terms of delta x goes to 0, right, then this is essentially in limit delta x tends to 0, 1 by b minus a, and a summation of I going from 1 to n, f of xi, that is, we are summing over the value of the function in each of these tiny rectangles, and then multiplied with delta x. As you can see, in the limit delta x tends to 0, this is nothing but the integral, right? So then that's 1 minus b minus a integral a to b f of x dx, right? And we started with the average value, right? This is the average value that we started with, and we have shown that the average value is equal to this. The average value of a function is 1 over b minus a f of x dx. So with this, let's try to see what curl means, right? So to do this, what we are going to do is we are going to take a tiny element. Let's say we're going to take just xy plane here. We're going to take xy plane, and let's take a tiny element, right? Let's say this point is xy, and this point is x plus dxy, and this point is xy plus dy, and this point is x plus dx, comma y plus dy, right? And I want to integrate some vector field. Let's say that vector field is f, right, along a path that goes from, let's say, point A here to point B, and from point B to point C, and from point C to D, and back to A. So I want to perform this integral over path ABCD. So if I want to do that, dr over ABCD, then first let me consider just the AB segment, right? So what we had just seen is that if I have A to B, f of x dx, right, that is equal to f average times b minus a, right? So if I want for this segment, for segment A to B, right? So from segment A to B, I'm trying to compute the path integral for a tiny surface element that's going from xy to xy plus dy to this and back here. So I'm starting with the segment AB. I have f dot dr, right? And because we have a dot product here, we are going to only take certain components. For example, along A to B, only y is changing. X is constant, x remains x. Only y is going to y plus dy. So I need to bother about only the fy component, really, right? And from here, because I'm looking at only the fy component, I can just take fy xy, right, on average, right, times dy. So we're taking the average, right, Fy, the average of these forces, and we are equating that to Fy dy. Similarly, if I look at segment CD, going from C to D, f dot dr, again only y is changing. So if I want the average, how did I get? Let's take a step back here. Sorry about that. Let's take a step back here, and let's see how I substituted f of xy for the average, right? This is ideally supposed to be f average times dy, right? How I substituted f of this for f average, let's see that. So if I want to take the average, let's for example take the value of f at point A. The value of f at point A would be f at xy, right? And the value of f at B would be f at x y plus dy. So then I can write f of B as f of xy using a simple Taylor expansion plus dou f by dou y, right, times dy at xy. Right? So if I want the average at A and B, I add f of A plus f of B by 2 to get the average. So that would mean f of xy plus this terms plus another f of xy plus this differential term dou of dou y dy, right, divided by 2, right? So this gives me the average, but I'm going to multiply whatever is this average with the dy. So I have another dy here, so I'm ignoring this term because dy times dy would be even smaller, dy square. So and this is f of xy plus f of xy, which gives me 2 f of xy divided by 2. So I'm canceling it out. So here we are ignoring this term after multiplying with dy. That is important thing to note, right? So for writing the average force, we are writing this term dy, but when we multiply it with this extra dy, which comes from b minus a here, then we are ignoring this higher order term. So that's how I can write f dot dr going from a to b as f of y xy dy, right? Similarly, I can write, again, let me draw it here. So we have a at xy, and then I have xy plus dy, that is b, and then I'm going to c, which is x plus dx and y plus dy, and then I have d, which is x plus dx and just y, and then back. So as we have seen on the last slide, going from, we're looking at the overall f dot dr over ABCD, and to begin with we looked at going a to b f dot dr. Here only y is changing along this direction. So from our theorem we had dy, and we substituted this f average, and f average was f of a, f at a plus f at b divided by 2 times dy, and f at a is simply f at xy because that's the coordinates here, and this is f at x comma y plus dy divided by 2 multiplied by dy. If I Taylor expand the second term, then I'm going to have f at xy plus dou f by dou y at xy times dy, right, divided by 2 times dy. So if I multiply this entire thing by dy, I'm going to get a second order term, dy squared. So I'm going to ignore that second order term, and these 2 f of xy's dy by 2 is what I would have, or I would just have f of xy dy. And all these are along the y-axis because we have change only along the y-axis while going from A to B. Okay, so that's how we got the first segment. For the second segment, I can write similarly. That is, let's say going from C to D. So if I'm going from C to D, I can write f dot dr going from C to D in a similar fashion, but now my coordinates are different. I'm going from x plus dx y plus dy to x plus dx comma y, and I'm going in the opposite direction. So my net change is minus dy, right? And by the same logic, I'm going to write this as fy x plus dx comma y, right? So similarly, I can write the terms for BC and AD, the top ones here. X is changing, not y, right? So if I look at the term for AB plus CD, while going from AB plus CD, for AB I had Fy at xy dy, and for CD I had minus dy Fy at x plus dx comma y, right? So then if I take the difference for AB and or add AB and CD terms, this is what I would get. I would get Fy at xy minus Fy at x plus dx comma y divided by dx, and here I would have dy. Sorry, I have no dx here. My bad. So I have only dy. I was getting ahead of myself. So I can then divide this by dx. right? And also sort of multiply it with dx there. So then I would have this term be, if you look at this would be simply dou fy over dou x dx dy. Similarly, if I look at the horizontal, if I look at horizontals there, I would have x changing, not y changing. So there I would essentially get dou minus dou fx by dou y dy dx. This is for BC plus DA. So we have ABCD, right? ABCD. So this is for AB plus CD, and this is for BC plus DA. We're trying to see the path integral going around the loop ABCD. So then if I want the total integral around ABCD of f dot dr, then what I'm going to get is this term dou fy by dou x minus this term dou fx by dou y dy dx, right? You can see that this is the curl along curl of f along the z direction, right? If you do the curl of f along the z direction, you get this term. So essentially, that's why we say curl is telling you literally how the field is curving around. We went around this tiny loop ABCD because we wanted to look at microscopically how the curliness of the field is. Remember, we don't want to explicitly introduce any surfaces. We want to look at each point. We want to describe the flux and the flow and the field at each point, and that's why we are introducing these terms like divergence and curl. And here we're looking into the fundamental, the physical interpretation of curl. So if I take a vector field like F and I went around the loop ABCD, which is a tiny loop that has the dimensions of delta X, delta Y, then I can see that if there is curliness to this, then this is non-zero, right? So that's exactly what curl is telling us. The curl does give us an indication for the curliness of the field, because if you take a point, this is precisely what we mean by curliness. That this if curl is zero, the line integral around this region would be zero. That is, this line integral of f dot dr would be zero. If this is zero, that means there is no curling of the field, because that's what it would imply about f. So curl f is really telling us about how we are getting this uh, uh, this line integral, right? So then I can write that from what we have seen, if I go around a path like ABCD, in general I'm going to call it a path, and I do f dot dr, I can show that this, if I do this in the xy plane, for example, then I would get curl of f in the z-axis dx dy, right? So then I can to show that this dx dy, we can write this further as curl of f dot dA of this contour that we have taken. Recall that if I have taken an open surface, right, the contour, if I traverse the surface this way, the area vector, if I traverse this way, the area vector is going to point this way out, right? Using the, sorry, if I go this way, it's going to point the other way. My apologies. If I curl our right hand fingers around the loop, right? If I do this, if I go this way, right, then it's going to point that way, correct? Along z direction, and that's why we are getting here curl of f z dx dy. So then I can write this as curl of f dot product with dA, right? So if I do that dA, then I get the component along z here, as you can see, because these are xy axis. So the area vector would be pointing perpendicular, normal to the surface along the z axis, right? And then essentially I am getting this on surface defined by the path. This is around the surface defined by the path. That is this surface. And that is essentially Stokes' theorem and also the fundamental definition of curl. So just like in case of divergence where we divided a potato into small volumes, if I have any sort of surface, for example, let's say in the xy plane, if I have a surface like this, I can divide the surface into small tiny integrals like this, right, that are going around. Um, just like how we divided the volume into cubes, we can divide this into tiny loops, right, and sum those loops up. So what we are saying is, if you want to get this f dot dr for the path for the entire this thing, right, then essentially what you're doing is you're doing this curl f dot dA for each of these surfaces and then adding them up in the surface. Just like how the volumes canceled out while we were discussing divergence, the insides of this cancel out, because if I take two loops, if I say I'm going like this in a loop and the next loop is going to look like this, so these two things would cancel out. So if I extend those loops along this direction or this direction, all the inside entities cancel out, giving me only the outer path boundary, and that is the surface defined by the path. So this is the fundamental definition for curl. So if we want to really write the fundamental definitions for integral definitions for curl and divergence, we could do that here. Just like how we have seen in terms of Gauss's theorem, we can write the fundamental definition for uh, divergence as divergence of J is equal to the surface integral of sorry, let me rewrite that. So the fundamental definitions can be written for divergence and curl, and I'm just trying to go back here in the slide. You will not be seeing it in the recording. Just give me a moment here so that I can write them down without any confusion. So I can write the fundamental definition of divergence of J or del dot J as limit delta V tends to 0, the flux about a tiny surface S delta V, surface enclosing this delta V. So if I have a potato and I divide it into small cubes, this is the delta V. The surface enclosing that is this S delta V. I'm taking flux along that and dividing it by delta V. So that's a fundamental definition for divergence. And similarly, we can write the fundamental definition for curl by looking at Stokes' theorem, where we have shown that if I go around a path and do the line integral f dot dr, essentially what I am getting is the surface defined by that path, curl f dot dA. Right. So this leads to Gauss's theorem, and this is Stokes' theorem. Right. So we will stop here for this lecture and continue about curvilinear coordinates in the next chapter.